So this is an introduction to the force table, and so what this accomplishes is allows us to get a visual representation of vectors as they apply their various forces at different angles and different magnitudes of those forces. So let's take a look. So when we look from above, what we see is that we have four pulleys, and each of these pulleys represent the location of our vectors. So they've been prearranged here to be basically at 90 degrees to one another: 0, 90, 180, and 270. And there's really two different ways to read the angles. There's either the inner numbers or the outer numbers. It really doesn't matter which way you do it. But if you want to be consistent with math class and you take 0 degrees to be to your right, then that would be the inner numbering system, as you see, 10, 20, 30, 40, and so on. And these are calibrated in precision of 1 degree increments. However, your eyes are probably good enough to estimate to half a degree, so that's what we're going to be doing in this lab. Now, all of these have the same amount of mass hanging from them, which is 50 grams. That's what the hangers represent. And their placement and their masses show you that they're basically in equilibrium with one another. And the way that you know that is you look at this central ring. And if this ring is equidistant around this pin, then we know we have equilibrium. In point of fact, we can remove the pin and nothing would happen. We're just going to leave the pin in there, and we're going to use that as a point of reference, so that if that pin is equidistant from the ring, or the ring is to say concentric around the pin, then you know that you've achieved equilibrium. And that's really the goal here with this force table. Now, you're not going to start out with 4 pulleys. We're going to start out with 3 pulleys. So what we're going to do is we're just going to remove the action of one of the pulleys for now. And let's say that all we had to deal with were 3 pulleys. That is to say, 3 forces. So we're going to leave this pulley and this pulley at their given locations for the moment, basically pretty close to 0 degrees and 90 degrees. And you can see that we're no longer in equilibrium. So that means what we're going to need to do is we want to take our third pulley and we want to adjust his location such that it balances the effect of the other 2 forces, or the locations of the 2 pulleys along with their masses. And so the way that we can achieve that is we loosen the pulley from underneath, and then we move the pulley around while at the same time applying some hand tension until we find a location. So let me get in the right frame here. So what I'm doing is I'm moving the pulley at the same time I'm adjusting with hand tension, such that when we look at the ring itself, we have found the appropriate location for where we're eyeballing that the third pulley location is correct. So it looks like we're pretty close, right about there. Then we release the hand tension and you see that we're no longer concentric about the pin. So now what you do is you take your weight set, and we want to add mass. Now that we have the correct location, we want to add mass until we find the appropriate amount that brings us back to equilibrium. So you adjust back and forth until you find that point. And we're pretty close there. And so now we see that we have brought ourselves back to equilibrium. A little bit of play, even though these are so-called frictionless pulleys, there's a little bit of play there. So that's a source of error, of course. But we see we're pretty close to that location. Right about, if you're looking at the inner ring, pretty close to 226.5 degrees. So our vector here, would be the amount of mass at that particular heading, which balances off the effect of the other two. And so now we have a balanced system. And so the terminology that goes with this vector would be known as the equilibrant, because it has equalized the effect of the other two pulleys, our forces, and the sum of these two would be known as the resultant, the result of the original two pulleys. And in point of fact, if we were to go back to our original two and add them together, they would have the resultant would be nothing more than equal but opposite to the equilibrant. That is to say, we could remove these two and put one pulley here that would be the exact same mass as the equilibrant, but different by 180 degrees.